Hello everyone, welcome back to my channel Mana Concept Lab Pro. You are here to watch the DSA roadmap, right? But don't just watch it, follow it. And please bring your notes and pen before watching this. Because watching gives you knowledge, but following gives you results. Before we get started, take a moment to hit the like button and support the channel. If you find this video helpful and valuable, don't forget to subscribe and turn on the notification bell for more content like this. Your support motivates me to create more educational videos and bring you useful content regularly. Now, without wasting any time, let's get started. If you are a beginner in programming or if you are preparing for coding interviews, competitive programming, placements, or just want to become better at problem solving, then data structures and algorithms is one of the most important topics you need to learn. And I divided this roadmap into 6 phases. But the problem here is many students do not know where to start. They randomly jump from arrays to graphs, then from dynamic programming to trees, and after some time they feel confused and demotivated. So in this video I am going to give you a complete DSA roadmap step by step from absolute basics to advanced topics. By the end of this video you will clearly understand what to study first, what to study next, and how all the topics are connected. Here comes the phase 1. It is all about picking one language, learning fundamentals, knowing object-oriented basics, and understanding purpose of data structures. Before starting DSA, you need a strong foundation in programming. DSA is not just about memorizing algorithms, it is about writing logic, understanding how the data is stored, and solving problems efficiently. So, the first step is choosing one programming language. You can choose C++, Java, Python, JavaScript, or any other language. But my advice is simple: choose one language and become comfortable with it. If your goal is competitive programming or placements, C++ and Java are very popular choices. And if you are a beginner and want something easy to start with, Python is also a great option. But remember, the language is only a tool. The real skill is problem solving. Once you choose a language, learn the programming fundamentals. You should understand syntax, variables, data types, loops, conditionals, functions, and basic input-output. You should also know how to write the pseudocode. Here, pseudocode means writing the logic of a program in simple English-like steps before writing the actual code. For example, if you want to find the largest number in an array, first think like this. Start with the first number as the largest number, go through the every number. If you find a bigger number, update the largest one. At the end, print the largest number. This is a pseudocode thinking. And you should also learn basic object-oriented programming concepts like classes, objects, inheritance, encapsulation, and polymorphism. You do not need to become an object-oriented programming expert before starting DSA, but you should understand the basics of it. Then comes the introduction to data structures. A data structure is simply a way to organize and store the data. For example, if you want to store a list of student marks, so you can use array. If you want to process tasks in order, you can use queue. And if you want fast searching, you can use a hash table. So data structures are very important because the way you store the data affects how fast your program runs. So phase 1 is all about building your base. Choose a language, learn programming fundamentals, understand pseudocode, functions, object-oriented programming basics, and get introduced to what the data structures are. Now we move to phase 2. This phase is very important because here you will start learning actual data structures and algorithm analysis. First, learn basic linear data structures. Linear data structures store the data in a sequence. The most common ones are arrays, linked list, stacks, queues, and hash tables. Let's understand them one by one. An array is a collection of elements stored in continuous memory locations. It is very useful when you want to access elements using an index. For example, if you have an array of numbers, you can directly access the third number using its index. Arrays are simple, fast for access, and used everywhere in DSA. Next is linked list. A linked list is made of nodes. Each node contains data and a reference to the next data. I mean, and a reference to the next node. Unlike arrays, linked lists are not stored continuously in memory. They are useful when you need frequent insertion and deletion. Then comes the stack. A stack follows LIFO principle. Last in, first out. Imagine a stack of plates. The plate you put last is the first one you remove. Stacks are used in function calls, undo operations, expression evaluation, and backtracking. Next is queue. A queue follows FIFO principle. First in, first out. Imagine a line of people waiting for tickets. The person who comes first gets served first. Queues are used in scheduling, BFS, and many real-world systems. Then comes the hash table. A hash table stores data in a key value pairs. It allows fast searching, insertion, and deletion on average. And hash maps and hash sets are extremely important for solving coding problems. After learning these data structures, you must understand algorithmic complexity. This is where many beginners struggle, but it is very important. Algorithm complexity tells us how efficient our code is, and there are two main types here: time complexity and space complexity. Time complexity tells us how the running time of an algorithm grows as input size increases, and space complexity tells us how much extra memory an algorithm uses. For example, if you search for an element in an unsorted array, you may need to check every element. So the time complexity here is order of n, which means linear time. And if you use binary search on an sorted array, you need to divide the search space by half every time. So the time complexity here is order of log n, which is much faster. And you also need to understand asymptotic notations. Big of O represents the upper bound or worst case growth. Big of theta represents the tight bound or average exact growth. And big of omega represents the lower bound or the best case growth. For interviews and coding practice, big of O is used the most. You should also learn common run times. Order of 1 is constant time, order of log n or logarithmic time, order of n as linear, order of n log n as efficient sorting, order of n square is quadratic time, order of 2 power n is exponential time, and order of n factorial is factorial time. Understanding complexity helps you write the better and faster code. Coming to phase 3, basic algorithms. After learning basic data structures and complexity, move to basic algorithms. The two most important categories here are sorting and searching. Sorting means arranging data in a specific order, usually ascending or descending. Start with simple sorting algorithms. Bubble sort compares adjacent elements and swaps them if they are in a wrong order. It is easy to understand but not efficient for large data. Insertion sort builds the sorted array one element at a time. It works well for small or nearly sorted data. Selection sort repeatedly selects the minimum element and places it in the correct position. These three sorting algorithms are simple, but they are usually order of n square. So they are not very efficient for large inputs. Then learn advanced sorting algorithms. Merge sort uses divide and conquer. It divides the array into smaller parts, sorts them, and merges them back. Its time complexity is order of n log n. Quicksort also uses divide and conquer. It chooses a pivot and places smaller element on one side and larger elements on the other side. Average time complexity is order of n log n, but worst case can be order of n square. Heap sort uses a heap data structure. It also has order of n log n time complexity. And after sorting, learn searching algorithms. Linear search and binary search. Linear search checks each element one by one. It works on both sorted and unsorted data, but its time complexity is order of n. Binary search works only on sorted data. It repeatedly divides the search space into half and its time complexity is order of log n, which makes it very powerful. And binary search is one of the most important algorithms in DSA, so practice it properly. Do not just learn simple binary search, also practice variations like first occurrence, last occurrence, lower bound, upper bound, and binary search on answer. Now we move to the phase 4, which is nonlinear data structures. Unlike arrays, linked lists, stacks and queues, nonlinear structures do not store data in a simple sequence. The two most important topics here are trees and graphs. First, learn trees. A tree is a hierarchical data structure. It has nodes and the top node is called the root. Each node can have child nodes. Start with binary trees. A binary tree is a tree where each node has at most two children. Then learn binary search trees, also called BST. In a BST, the left child contains smaller values and the right child contains larger values. This makes searching efficient if the tree is balanced. Then learn AVL trees. An AVL tree is a self-balancing binary search tree. It keeps the height balanced so operations remain efficient. You should also understand heaps. A heap is a special tree-based structure used in priority queues. In a max heap, the largest element is at the top, and in a min heap, the smallest element is at the top. Then learn tree traversal. Traversal means visiting all nodes of a tree. The main traversals are in order, pre-order and post-order. In order is left, root, right. Pre-order is root, left, right. And the post-order is left, right, root. Also learn level order traversal, which uses BFS. After trees, move to graphs. A graph is a collection of nodes and edges. Graphs are used to represent networks like roads, social media connections, computer networks, and maps. There are directed graphs and undirected graphs. In a directed graphs, edges have direction. For example, A points to B. In an undirected graph, edges do not have direction. A is connected to B and B is connected to A. The most important graph traversal algorithms are BFS and DFS. BFS stands for breadth first search. It explores nodes level by level and uses a queue. DFS stands for depth first search. It explores deeply before backtracking and can be implemented using recursion or a stack. After BFS and DFS, learn shortest path algorithms. Dijkstra algorithm is used to find the shortest path in a graph with non-negative weights. Bellman-Ford algorithm can handle negative edge weights. A-star algorithm is commonly used in pathfinding like maps and games. Then learn minimum spanning tree algorithms. A minimum spanning tree connects all nodes with minimum total edge weight. The two main algorithms are Prim's algorithm and Kruskal's algorithm. This phase is very important because trees and graphs appear frequently in interviews and real-world systems. Before we move further, I have a teeny mission for you guys. If you are finding this roadmap useful, hit the like button. It won't reduce your battery percentage, I promise. And if you haven't subscribed yet, what are you waiting for? The subscribe button is feeling lonely down there. Give it some company. Also share this video with your friends who keep saying, bro, where do I start DSA? And most importantly, drop a comment below. Tell me that what roadmap you want next or which concept you would like me to explain. Your comment might become my next video idea. Enough talking. Let's get back to roadmap and continue the journey. Now phase 5. Once you are comfortable with basic and nonlinear data structures, move to advanced data structures. These are useful for advanced problem solving, competitive programming and system level understanding. First learn trie. A trie is a tree-like data structure used for storing strings. It is commonly used in autocomplete, dictionary search and prefix-based problems. Then learn segment trees. A segment tree is used to answer range queries efficiently. For example, finding the sum, minimum or maximum in a range. It can answer queries in order of log n time. Fenwick tree, also called binary indexed tree, is another structure used for prefix sums and range queries. It is simpler than segment tree but supports fewer operations only. Then learn disjoint set, also called union find. It is used to manage connected components. It is very important in graph problems, especially Kruskal's algorithm. Then come suffix trees and suffix arrays. These are advanced string data structures used for pattern matching and substring problems. After that, you can explore complex data structures like 2 to 3 trees. B trees, B plus trees, skip lists, and so on. B trees and B plus trees are especially important in databases and file systems. They help store and search large amounts of data efficiently. Skip lists are probabilistic data structures that allow fast search, insertion, and deletion. Indexing is also important, especially if you are interested in databases. Linear indexing stores indexes in a simple sequential way. Tree-based indexing uses tree structures like B trees to speed up search operations, and this phase is not always required for beginners, but if you want deeper knowledge, advanced interviews or competitive programmings, these topics are very useful for you. Now comes the final and most important phase, which is problem solving techniques. Knowing data structures is not enough. You must know when to use them, and this is where algorithmic patterns help you a lot. Start with the recursion. Recursion means a function calling itself. It is used in trees, graphs, backtracking, divide and conquer, and dynamic programming. Then learn brute force. Brute force means trying all possible solutions. It is usually not efficient, but it helps you understand the problem. After brute force, learn backtracking. It is used when you build a solution step by step and undo choices when they do not work. It is used in problems like n-queens, Sudoku solver, permutations, combinations, and subsets. Then learn greedy algorithms. Greedy means choosing the best option, the best option at the current step. It works when local optimal choices lead to a global optimal solution. Examples include activity selection, fractional knapsack, and some graph algorithms. Next is divide and conquer. In this technique, you divide the problem into smaller subproblems and then solve them and combine the results. Merge sort and quicksort are classic examples for this. Then comes dynamic programming. It is one of the most important and difficult topics in DSA. It is used when a problem has overlapping subproblems and optimal substructure. In simple words, if you are solving the same subproblem again and again, store the result and reuse it. Start DP with simple problems like Fibonacci, climbing stairs, house robber, and coin change, and then move to 2D DP, subsequence problems, knapsack, longest common subsequence, and matrix DP. After DP, learn two-pointer techniques. It is useful for arrays and strings, especially when dealing with sorted data or pairs. Then learn sliding window. It is used for subarray and substring problems. For example, maximum sum subarray of size k, longest substring without repeating characters, and minimum window substring. And next, fast and slow pointers are used mainly in linked list and cycle detection. Next, cyclic sort is useful when numbers are in a specific range, usually 1 to n. And then merge intervals is used when working with overlapping intervals. And next, two heaps are used when you need to track median or balance two groups of numbers. Next, kth element pattern is used to find kth largest or kth smallest elements. Then island traversal. It is used in grid problems, usually with DFS or BFS. And then randomized algorithms use randomness to make decisions like randomized quicksort. Last, multi-threaded patterns, which are more important and more advanced and useful when dealing with concurrent programming. Here, the key in this phase is practice. You should solve problems pattern by pattern. Do not randomly solve 500 problems without understanding, and instead learn one pattern, solve 10 to 20 problems on that pattern, then move to the next pattern. Now let me tell you how to actually practice this roadmap. First learn the concept and then implement it yourself. After solve easy problems and medium problems and then revise after a few days. For every topic follow this method. For example, if you are learning stacks concept, first understand what a stack is and then implement stack using array or linked list and then solve easy stack problems. Then solve medium problems like next greater element, valid parenthesis and monotonic stack problems. Also do not ignore dry runs. Dry run means manually tracing your code with sample input. This improves your logic and debugging skills. Another important thing is consistency. DSA cannot be completed in 1 week. If you are a beginner, give yourself at least 4 to 6 months. Study daily even if it is only 1 or 2 hours. Consistency matters more than speed. If you want a rough timeline, you can follow this. In first month, programming fundamentals, arrays, strings, linked lists, stacks, queues and complexity. In second month, complete searching, sorting, recursion, hashing and basic problem solving. In third month, complete trees, binary search trees, heaps and graph basics. In fourth month, complete graph algorithms, greedy algorithms, backtracking and divide and conquer. In fifth month, complete dynamic programming, tries, segment trees and advanced patterns. In sixth month, do revision, mixed problem solving, mock interviews and advanced topics. This timeline is flexible. If you are a complete beginner, take more time. If you are already known programming, you can move faster. One more thing I would like to tell you is dynamic programming becomes easier when you look for repeated subproblems. You can follow these steps. First, brute force, memoize, tabulate, and optimize. Follow these steps and you will crack dynamic programming very soon. Finally, guys, I covered all the topics in this roadmap of DSA from the fundamentals to the advanced topic in 6 phases. Here is the full path. And before ending the video, let me also tell you some common mistakes. The first mistake is jumping directly to advanced topics. Do not start with dynamic programming or graphs if you are not comfortable with arrays and recursion. The second mistake is only watching tutorials. Watching videos feels productive, but real learning happens when you write code yourself. The third mistake is memorizing solutions. In DSA, understanding the pattern is more important than memorizing code. The fourth mistake is not revising. You may understand a topic today, but if you do not revise, you will forget it. The fifth mistake is comparing yourself with others. Everyone learns at a different speed. Focus on your own progress. So this is the complete DSA roadmap. Start with programming fundamentals, then learn basic data structures like arrays, linked list, stacks, queues and hash tables. After that, understand time and space complexity, then move to sorting and searching. Then learn trees and graphs. After that, explore advanced data structures. Finally, master problem solving patterns like recursion, backtracking, greedy algorithms, divide and conquer, dynamic programming, two pointers, sliding window, and graph traversal. Remember, DSA is not about finishing topics quickly. It is about building problem solving abilities step by step. If you follow this roadmap consistently, practice regularly, and revise properly, you will definitely become strong in DSA. That's it for this video, guys. If you found this roadmap helpful, like the video, share it with your friends, and subscribe to the channel for more programming and placement preparation content. Thanks for watching, and I'll see you in the next video.